Take that on next Tuesday.
Next Tuesday.
Okay,
Next
sir.
Tuesday, what time you will have time? Like during the class hours is too small, 1 hour. You may need longer time.
Afternoon session, sir. 2 to
Afternoon,
5.
2 to 5 is okay?
Yes, it's okay, mostly.
Okay. So next Tuesday is 3rd of October. So let's go ahead with 3rd of October. 3rd of October, 2 to 5. 3 hours. You can actually, in the afternoon, you can elongate it. And for my part, the syllabus is Maxwell Boltzmann distribution. And imperfect gas.
Yes, sir. Oh, no, no, no.
That means what I will be covering until today. Okay. And Nirvay sir will discuss what he is going to be covering. So maybe it will be from the end of quiz 1 to uh, the next class or something. It will be like last time. So we will give you the PDF file. You have to write it in the paper with your own handwriting and then scan it and send, upload it in the Google Classroom. Because Google Forms are, they are, the subjective questions are very difficult to ask. Here you have to do the maths by your own, what value you are putting, you wanted to see. In Google Form, you're just giving the final answers. So then it's not very good evaluation. So it will be like last time.
Sir, do you know about final exams?
Final exam is going to be starting from 18th of November. So we'll reserve the class before that. Maybe in the first week or before 10 your class will all be, I don't think we'll take class. I will take only one class which will be on 3rd. Next Tuesday will be my last class.
Okay, what might be the mode of examination, like through Google
That
Forms, sir?
it's not yet. It will be online. That much we have heard, but we don't know now. So we'll let you know. Maybe it will be like this. What we are doing.
Okay, sir, thank you.
Yeah. So it's preferably that it will be like this. Okay. So in the last class, we had seen that for imperfect gases, we had to make from the ideal gas equation, we had to make some correction. Like your ideal gas equation was for 1 mole, it was PV equals to RT. Now, since this is the ideal gas equation. Now, because the molecule will have some finite size, therefore, all the volume are not available for other molecule, all the other molecule to have their random motion, and That's why the volume available is different. So we are seeking for correction such that we can write the equation in the following form. It's like this. Oh, sorry. There will be correction for pressure and there will be correction for volume. And last class we had seen that delta V equals to minus B, where B is the amount of volume which is not available for the molecules we have. They are random, they are not free. They are finite size. Due to this, we have this correction term. Now today we will see the correction due to intermolecular attraction and which will lead to a correction in the pressure. In kinetic theory, we had assumed that the molecule, whatever we have, they don't possess any potential energy. That means the molecule-molecule interaction was neglected. But it is not the case. We have to correct for that. So imagine one molecule is sitting here. You have this molecule, and there are many other molecules everywhere in deep inside the container. So to this molecule, all the attractive force are like this. So if you take the vector sum, so it vanishes. It will be a 0. So molecule sitting deep inside the container, the net attractive force due to other molecule is 0. However, if the molecule is on the side of the container, let's say here is the side of the container and you have the molecule there. But here the forces acting on this side, okay, but you have some imbalance. So that leads to a net force, net attractive force acting on that molecule. So whenever a molecule tries to strike the wall of the container, the net momentum transfer dp dt is equals to force. So since it has an imbalance force, so the net momentum transfer, it needs to be recalibrated. That's how we had derived the pressure, and it will be less, and that will result in a decrease in the pressure. And the drop in pressure is known as some cohesive pressure and something like that, because as the intermolecular force holds the molecule inward, so the net momentum change in reality is actually more, because it had to overcome this intermolecular force. So that's why when we discussed, when we derived the pressure, we had actually underestimated the pressure. We have to add, because our actual pressure is more. And if the correction is delta P, as we said, and we call this A. Therefore, correction in pressure is A over V square. So combining both the correction for pressure and correction for volume, we can write the equation as this is the correction for pressure and this is the correction for volume, and we had RT on the other side. We arrive at this equation, equation 1, and this is known as van der Waals equation. This A and B are van der Waals constant, and van der Waals assumed that A and B are same for all the gases, but it is not the case. Also, he assumed that it is constant, but later on it is found that A and B also vary with temperature. Nonetheless, now we can compare how it is like from the ideal gas equation, which was like a rectangular hyperbola. How, let us see how it can explain the behavior at low temperature. For that, we have to be this side. We draw the isotherm P on the x-axis.
Sir, excuse me.
Yep.
Sir, can the constants can be negative?
B, if you have B is negative, then that means you don't have any the molecular volume, whatever finite size is negative. That is not possible. And here A is like proportional to n square. So n square cannot be negative, right? So A and B should be positive.
Okay, sir.
Otherwise, it will lead to a unphysical solution. Suppose your A is negative, then it will give you some, or B is negative. Okay, in that sense. Let us not complicate. So, your pressure is proportional to n square. So, the correction cannot be negative. So, A is positive, and also B is your available volume, which is unavailable for the other molecule. It comes from because the molecule has finite size. So, it should be positive.
Thank you, sir.
Okay, let us draw this. how it goes. So before I draw this, let us rewrite the equation in other form. Then you will be able to appreciate how to, or I should write first. Then you can correct it. I can connect it properly. So this was the region where we had mixing, like condensation was happening for real gases. Now, Van der Waals equation explains properly this part, which is above the critical temperature, which are like this, ideal gas behavior. Then at low temperature, comes like this. It's a cubic equation. I'll show you. Then it will have free value. This is how the Van der Waals equation write it's like that, and these roots they actually comes closer, and at here it behaves like this. So this is like Tc, this one as T1, this one as T2. The hierarchy in temperature is this. So Van der Waals equation looks something like this. So it's qualitatively is very similar to the real equation curve, but there is some maximum minima occurring here instead of a flat part. So if we rewrite the Van der Waals equation, you can write it like this. You can open the bracket and Van der Waals equation because P plus A over V square. I take it like this, V minus P. Take it on the other side, or you can do it RT over V minus B minus A over V square. And if we take the LCM and all, finally you can write it like this. VQ minus VB plus, I think the coefficient for V square. So this is true. So you see that the Van der Waals equation is cubic in V. So it will have three roots. One, or at least one should be real, other two can be imaginary or complex. But that means it's for one value of V, it should give three values of P. So you can see. So that's 3, 1. If you take one value of P, it should give three values of V. 1, 2, 3. Take a straight line and see. So there are these three roots. As temperature increases, these roots they approach one another and they become equal at T equal to Tc. So all these roots they approach each other towards, and then coalescence become one root at T equal to Tc. That is why this point is called the critical point, and the temperature is critical temperature. Approach each other as temperature increases. And become 1 at T equals to Tc. This point is called critical point. That means the pressure is the critical pressure, temperature is critical temperature, and volume is critical volume. Also notice that in the limit b tends to infinity and b is very large, b is very small. And also when b is very small, when b is very small, b is very high. But this b cannot be less than d. This will lead to negative pressure that as we discussed. So although this van der Waals isotherm resembles the real gases, but there is a difference in detail as it has maxima and minima. We can find the position of this maxima and minima. Instead of a straight line, it has maxima and minima, where vapor between phase coexist in real gases. That was one of the striking difference. So to find this maxima and minima, we have to take, in isotherm, we have to take the first derivative to be 0. Minima, you set this del P at constant temperature, you take only one curve equals to 0. So this will give you the position of maximum minima, and del T you take it from this equation 1 or equation 2. It's easy to consider from here. Let us take del T from this equation. And this will be, it will stay as it is, minus sign because P is at the denominator. Then 2 will be plus. So set this to be 0. And solve for T in this equation. So let's say this is 3. Now you eliminate T from this to this, equation 2. Then we will get pressure to something like this. R over B minus B, then you have your T. B minus B square, RB2. Then you have square on the other side. Now you have to simplify this. Your R goes out. Your B minus B gone. So twice A B minus B over VQ is A over V square. Okay. We have some simplified form. Now if I take the LCM to VQ, B minus B minus AB. So K then VQ, B minus 2B over VQ. So this is B. Let us call this 4. So these are the position of maxima and minima. Which one is maxima, which one is minima? You have to take the second derivative to assert that this is the maxima and this is the minima. You can do it in similar way. But the most interesting thing is that at critical point, at critical temperature, uh, at this point all the root becomes equal. That means you don't have any maxima and minima. T equal to Tc, there is no maxima and minima, but you do have a change of stroke. So this point actually becomes an inflection point. And how do you find this? So let's take the second derivative. At this point, at t equals to Tc, it should be 0. That's the condition for inflection point. And the pressure, what we obtain, we will call this at critical pressure, and what volume we obtain, we will call that as critical volume. So second derivative, this is your first, we will use this equation 4, this one, which is easier. Then it will be A over, because it has, it will have two terms, one is V2, another one is like that. So we call this EC at T equal to at this point. See this equation. Now I can simplify this. Let's take this to the LCM. So we have this. 3x minus 2b equal to 0. Now BC is non-zero, so we can divide it by multiply by 0. Plus 6 AB equals to 0. And I'm solving for BC, so it will be 2. Then on the other side, that is BC with 3B. This is 5. Similarly, you can find TC, just use this equation for temperature, which is this equation 3, using 3. You can write this like this, and you plug this value, which is 3b minus b whole square r 3b cube, so b cube. This is 2b, therefore Tc is this. This is the critical temperature coming from van der Waals equation. And volume, temperature, and pressure. Pressure, you plug that in equation 4. Using 4, Tc this one. And we have to simplify this. This is 3b AB over 27 PQ. Therefore, is equals to A over 27 B square. This is 7. Now there is something called critical coefficient. Critical coefficient CS is defined like this. And if you take it for Van der Waals equation, it comes out to be 8 over 3. Van der Waals gases. And it is equal, it's constant, so it is equal for all gases according to Van der Waals. But in reality, experimental results shows that it varies from gas to gas, so it doesn't explain properly. So though it is a good approximation, but there are certain things which the Van der Waals equation cannot explain. So the limitations are the following. If I have to list out limitation of Van der Waals equation, first, like as I said, it fails to explain the qualitative detail. So qualitatively it is okay, but quantitatively it fails. The critical coefficient is not 8 over 3 for all gases, but it ranges from it ranges from 3.3 to 3.5 if depending on the gas. So it's like that. Therefore, to overcome some of the shortcomings which I have listed, some of the other equations which was proposed, I will outline some of them. Van der Waals equation. So I will just outline some of them. Just 1 second. I'll check the attendance. Okay, good. So first one of them was Clausius equation. Clausius equation. So he modified Van der Waals equation like this. So what it did is he replaced A with this A prime over D and taken an additional constant C. Added additional constant C. So this is the main difference with Van der Waals equation. But using this, there was no substantial advantage of this equation over Van der Waals equation. Though it corrects a little bit, but the correction is not substantial, particularly at temperature below the critical temperature. So there's another guy which you know his name is where Werkelton. Let me get the spelling correct. Whatever it is, it proposed that we don't need this C. If we write it just like this, it works fine. But this C is not doing much. So it is as good as not taking the V. This A prime over T is taken just to incorporate the temperature dependence within A. So it is assumed or it is found that it is somewhat proportional to 1 over T. That's why it's taken like that. So even if you take it the temperature dependence of the constant A, uh, though it though it improves a little bit, at least it gives a better agreement with experimental data than the Mandelbrot equation over a wide range of pressure. It fails badly near the critical point. Then later, Saha and Bose came up with their equation. They derived it from the thermodynamic consideration and from the uh, theory of probability. Their equation is much better than Van der Waals or this Clausius or Berthelot equation. It is the same Bose which is who named all the bosons after named. From his name, all the bosons are named as boson. It's the same boson. And this Saha was his classmate. And, and the Bose-Einstein statistics, which you will learn, it's named after this. So there is a lot of work on this. So the equation looks a bit complicated. T over twice B, then you have e power A over RTV, then you have ln. Ln is the log with base E. E minus 2P over V. Was derived considering thermodynamics and the theory of probability. And from this equation, uh, this equation predict the critical coefficient very close to what it is observed for real gases. In this, is a good agreement with experiment. Okay, I think I should stop it here. So your exam will be up to this, the quiz 2. All right. Any question?